Hi, everyone. So today I'm going to tell you about the effects of energetic events on the atmospheres of habitable zone planets orbiting M-stars. And here I'm going to focus these energetic events on the UV variability, including strong flares from the M-stars and how those impact the planet atmospheres. So to make sure that we're all on the same page, I just wanted to remind us all, even though I'm sure you already know, that M-star planets are ubiquitous, including terrestrial habitable zone planets. So if you work out the numbers based on the occurrence rates from Kepler's and the number of low mass stars in our galaxy, it turns out that there's about tens of billions of habitable zone planets in our one Milky Way galaxy, which is a wonderful statistic to know, and especially for those of us who are interested in understanding the distribution of habitable environments in our galaxy, then we really need to be focusing on the M stars because that's where most of them lie. So here's a plot that's just a flipped HR diagram to confuse you a little bit, showing you the luminosity and mass of FGK and M stars. And what you'll notice is that the M stars, the red points, span 3 orders of magnitude in luminosity and go in mass from 0.1 to about 0.6 solar masses. And the reason why I wanted to point this out is because we actually call them different things: early M stars, mid M stars, and late M stars. They're actually different beasts, and they have different evolutions of their UV emission. And they are different in their flare statistics as well. So when someone tells you that they have found a planet around an M dwarf, your first question should be, what kind of M dwarf is that? So here's a really interesting diagram that has a lot going on, and I unfortunately will not have time to talk about everything here, every arrow and its impacts on its planetary atmosphere. So I encourage you to take a screenshot. This was created by Evan Davis from VPL at the University of Washington, and I would love to spend hours talking over this with you, but we just don't have the time, nor do we even have the data to really understand this plot as well as we need to, and nor have the models really evaluated the full parameter space that we need to fully understand what's going on here. So I'm going to focus on the top part of this, looking at the stellar activity and its evolution from the pre-main sequence phase to the main sequence phase and so on, and very briefly show you some examples of the work that we've been doing with VPL in order to look at the impact of this variability on the planet's atmosphere. So if you take this, what I call an onion diagram of an exoplanet atmosphere, we typically break it up into 3 regions. We have the lower atmosphere, which is photochemically impacted by the near ultraviolet light as it propagates and is absorbed at those layers. In the upper atmosphere, which is this middle one, where the far UV photons from the central star get absorbed. And then the outermost region is the exosphere, and that's where the extreme UV and the X-ray photons are absorbed and can propagate mass loss and cause potential complete erosion of an exoplanetary atmosphere. Now for M stars, the habitable zone is very close. For Proxima b, it's only 10 stellar radii away from its host star. And so, which is very different than our comfortable 1 astronomical unit location from our sun. So at these distances, the atmospheric heating and escape by the extreme UV photons is going to be certainly something we have to keep in mind and understand better if we want to understand the evolution of the primordial atmosphere and the secondary atmosphere of the exoplanets. We also care about atmospheric photochemistry because they photodissociate the key molecules we're looking for. If you're looking for biosignatures in these planets, you have to understand what the far UV and near UV are doing to the molecules of interest. And of course, both these things will affect the surface habitability of the planet and the detection of any biosignatures, because it turns out that there is a pathway where the UV can create both false positives and false negatives of biosignatures in Earths around M stars. Here's something I wanted to point out that I'm not sure everyone really appreciates, is that even though M stars are intrinsically faint, they're fainter than their FGK counterparts, but to a planet in the habitable zone, they're UV bright. right? So there's more UV photons incident upon a habitable zone planet around an M star than there is around an Earth around a sun-like star. And this plot from Segura et al. 2005 shows this very clearly, where you have the sun here in the yellow curve, and in the far ultraviolet, specifically AD Leo, an active M star, and GJ436 are much higher, orders of magnitude higher in the far UV. And that's also the case for the extreme UV as well. I also wanted to point out this green curve that is a model of just the photosphere of an M star, which you might see in the literature as called non-active star. And in reality, there's no such thing as a non-active M star. So these models are always going to underpredict the near UV and the far UV of an M star. And so we've worked to actually rectify this and produce a new set of models that are empirically guided by the observations I'm about to show you. So here is a plot from Peacock et al., and where they calculate a photosphere only model here in red. That's that non-active M star you might see in the older literature. And using our data, build new upper atmospheres onto these models so that they can reproduce the temperature pressure profile of the chromosphere, the transition region, and soon to be the corona of these M stars. And these are the really key wavelength ranges, as I pointed out, where the EUV heats and inflates the upper atmosphere, and the far UV and near UV drive the photochemistry. And this region in the middle here, where you have direct photoionization of the hydrogen in the primordial atmosphere, is really, really key, but also rather non-coincidentally, is absorbed by the interstellar medium. So we will have a very hard time observing the EUV in this range from 400 to 900 angstroms ever for the vast majority of exoplanetary systems. So especially those that are transiting, for which we will want transmission spectroscopy from. So finding ways to predict this by using the observations is really the strategy moving forward, and one that we have adopted. And if you're interested in using these models, they are archived at MAST, at the Space Telescope, under this URL. So you can find what we've done up there. This work is led by Sarah Peacock, who's now at Goddard. So to give you one example, and I have one at the end as well, here is a transmission spectrum of a habitable zone, modern Earth, around an M3 star, so a mid-M, that shows the effect of whether the star has 10 times the UV emission than some baseline here. And even though the observations are all done in the optical and infrared, the context of the UV is needed in order to interpret these longer wavelengths observations of the planets. And you could see that the methane is highly depleted in a high UV environment. And the same is true for water and so on. And I'll show you some other examples as well. So this should bring home the point that we're going to be collecting, hopefully, many spectra of Earth's inhabitable zones, one way or another, but we need the UV in order to understand them. So we started a few years back in order to help answer this question, the HAZMAT program. It stands for the Habitable Zones and M-star Activity Across Time, and with a goal of mapping the UV evolution across low mass star range, so going from late M's all the way to K stars as well. And to do this, we used the Galax Archive. Galax is the last UV explorer that NASA funded. It hasn't been functioning for a decade now, but it has left us with a lovely archive that mapped about 3/4 of the sky in the far UV and near UV photometrically. And we also have a couple of large programs from HST to do spectroscopy of both young, intermediate, and old stars, in order to look at the evolution of both the line emission and the continuum emission of these stars. And so putting the HAZMAT program into the context of the way we envision it is that we collect the data, as we have been, either using archived or new observations, and I'll show you even future observations that we're planning in a little bit. And then we build these new upper atmosphere models in order to get the full wavelength range all the way from the EUV to the infrared. And then we can irradiate model planet atmospheres with accurate data from the central star. And that's work being led by VPL, the VPL group run by Vicki Meadows and her team at University of Washington, and they do photochemical modeling and climate modeling of these planets. And then we will have actual spectra, good model spectra that are irradiated by actual empirically guided stellar data in order to interpret the spectra we hope to get back from future missions, like from JWST, LUVOIR, HABEX, and even the ground-based extremely large telescopes. So that's kind of the HAZMAT program in a nutshell. So I'll show you a few of the results very briefly. There are more papers out there than I have time to talk about, but one of the first results from back in 2014 is we looked at the evolution of the far UV and near UV using Galax photometry of a bunch of stars with known ages. These are known young moving group members. And so we know their ages fairly well. And we took about 20 or so targets of these early M stars per each age bin. And here I'm showing you just the median point of that entire distribution. So we can then look back and say statistically what a planet around an early M star might have been exposed to, especially in the early times when the emission was very high. So if you care about disk dispersal and giant planet formation, as I know you guys have been talking about this earlier this week, then you have some sense of what the UV environment was of the disk and the protoplanet at the time. When terrestrial planet formation happens and the primordial atmosphere is formed, what you see here is in these early Ms, the UV emission is not dropping nearly as quickly as it does for sun-like stars. And the same is true even for when the Earth's secondary atmosphere, we think, was developed between 50 and 500 million years. The UV emission is not going down as quickly as you might like. And it only starts dropping at around the age of the Hyades at 650 million years old, and so on. So if the secondary atmosphere survives, then maybe life might start evolving on the surfaces of these M stars. Now, as I said, each of these points is the median of a whole range of points, and the full range spans an order of magnitude at each age bin. And so this is probably due to variability, long-term cycles, randomly catching flares in the Galax data. But we're trying to understand the flares and the variability in order to understand this very real distribution. So the important thing is that not every M star is the same, and trying to understand your M star might be quite valuable. So to summarize a few of the, I guess, 3 of the HAZMAT papers where we published just the early Ms that I showed you. We also have one that has the early Ms and the late Ms, and then there's a summary one that's now coming out by my graduate student, Tyler Ritchie-Yowell. And she calculates here what is the far UV flux in the habitable zone for each of these spectral type bins. And it's not that different, right? So we have, of course, the late Ms do stay active a little bit longer, even increase as they contract onto the main sequence. But the early Ks and the early Ms are not that different from each other. And so we really need to be considering this history of every planet that we want to study around these masses. Now, moving on to some of the spectroscopy that we're able to get with HST. This is using the COS spectrograph. Here are just 3 examples of the spectra we collected in the far UV and in the near UV for 3 different ages: a 40 million-year-old early M star, a Hyades star, and a field star. And you could see that they do vary by an order of magnitude or so. And so I refer you to this paper by Park Lloyd, where he studies the evolution of the lines and the continuum with these ages for the entire sample. Now, another thing that we found, because we were spending a lot of time looking at these stars, not as much time as we would have liked, of course, but still these large programs did collect a lot of photons, was we were able to catch some flares. We have a bunch of flares in those data, but here is the record holder, something we call the HAZ flare, because it is a super flare that increased by a factor of 200 in about 200 seconds. And it's the kind of thing that happens every day on a young M star, every day. It's pretty remarkable, don't you think? And then more recently, just a few months ago, we published an observation from HST of a flare of Proxima Centauri, our nearest neighbor. And what you see here is an increase in the far UV continuum by a factor of 14,000. Now, the Has flare here on the left-hand side is in fact energetically greater. It's a stronger flare, but in a relative sense, this flare on Proxima Centauri is quite spectacular, 14,000. Now, this exact same flare, because we have simultaneous data with HST and TESS, increased by 14,000 in the continuum, 13,000 in the far UV lines, and only a factor of 10 in the optical. So this should make you wonder, all those optical flares that we've been seeing from Kepler and K2 and TESS and the ground-based monitoring programs, if you see a flare in the optical, what's really going on in the UV? And this is something we're trying to get a handle on. It could be the black body continuum associated with the flare. Here I'm showing you the full wavelength range from 500 to 4,000 angstroms. This is the Has flare data. So the blue here is the quiescent spectrum of that target. The orange here is the flare itself, the flare spectrum. And what we were able to do is fit a 15,000 Kelvin black body, which is a much hotter black body than we usually assume for the flares. Typically, we assume 9,000 Kelvin black bodies, but since we published this, 40,000 Kelvin black body was also reported for another M-star superflare. So when we're asking the questions of how much energy is actually being outputted in these flares, we still don't have a complete picture of that, and we're working to get those answers. So one thing that we like to do is we like to plot things into these flare frequency distribution plots. It's called, so we've got the frequency of the flares on the y-axis, and in this case, the far ultraviolet energy on the x-axis. And what I'm showing you is the difference between the old M-stars here in blue and the young M-stars from the HAZMAT program. These are just the early M-stars, I should say. Here in orange, anchored by the Has flare, the most energetic flare we have yet measured. That happens at about once per day. And you can see that these young M-stars do indeed flare more frequently and with more vigor, and with a super flare every day. And compared to the sun, this is a lot more energy and at higher frequencies as well than sun-like stars. So the question then is, what's really happening over here? What's happening in this range? How strong do these flares really get? How strong is a flare that happens only once a month or once per year? And these are really hard data to get at because we just cannot monitor these stars for long enough. Even the two large programs that we have with HST are still only about 2 weeks of HST time. So we're not even getting close to getting to the statistics of the once per month flare energies. And so I did tell you about these why UV matters, and hopefully you're convinced, and what we've managed to learn with existing instruments and data, but we don't have a way yet to get these very energetic but more rare flares. And so I'll tell you very briefly about two upcoming missions that we're trying to build in order to get these data. So the first one is SPARCS, the Star Planet Activity Research CubeSat. Now, this one is already halfway through development, funded by NASA through the APRA program, the Astrophysics and Research Analysis program. It's going to be a 6U, and a 6U is kind of like this big, about the size of a family-sized Cheerios box. It's going to house a 9-centimeter telescope, which we already have here at ASU, sitting in a fume hood, waiting for the camera to come from JPL. And then we're going to integrate it all at JPL along with the spacecraft. So we still have a bit more work to do there, but we're aiming for a launch in 2023. We're going to launch it to a sun-synchronous terminator orbit. That's the hope, at least. Of course, we'll be hitchhiking a ride, as these small satellites typically do, but that's what we're aiming for. It's going to do 2-band photometry simultaneously in the far UV and the near UV, so we will get flare colors. And the field of view will be 0.7 degrees, which means it's fairly big, and there'll be other stuff going on in the field, that another science we could pull out of there. And most importantly, we'll be staring at stars for about a month each star. So the goal is do it for 1 year so far, see how it goes, observe 20 M stars, very young stars, intermediate age stars, and old stars, very similar to the whole hazmat theme, and look for the evolution of the UV emission with flares. Now, the second mission is one that's under development. We're working to propose this to the upcoming MIDEX call with JPL. It's called UV Scope. It's the ultraviolet spectroscopic characterization of planets and their environments. The goal there is to actually do transmission spectroscopy in the UV of all sorts of planets, large and small. But part of the mission goals is also to then simultaneously characterize the UV emission from all the planet hosts of all the stars, of all the planets that we're going to be studying. And we will do this spectroscopically with a medium resolution mode in the far UV and a simultaneous low resolution in the near UV, covering all the way from Lyman alpha. So we'll be doing Lyman alpha transits to look for escaping gas, all the way to 4,000 angstroms. So we can then match it up also with things that will be coming from ground-based observations and from future space-based observations. This is our fabulous team. Names I hope some of you will recognize. And so keep an eye out for that. This will be submitted at the end of this year, and if all goes well, will be launched in 2028. So not too bad, not too far away. And so all of these data, both from SPARCS and from UV Scope and still ongoing programs with HST, are to help us understand the planet's atmosphere, both for large and small planets, but here's an example specifically for prebiotic Earth, right? This is showing you a model. Again, this is by Evan Davis and collaborators from VPL, where what we're showing here is these spaghetti plots, right? So the volume mixing ratios of key molecules of interest for biosignature work, right? And how they are changed, not because the planet itself has changed intrinsically due to any outgassing or anything like that, but rather because of the stellar emission. And so here, what we're showing is 650 million year old spectrum, something like GJ876. And as the star ages, moving towards the left-hand side, the impact on these molecules due to photochemistry is very clear and dramatic, especially in this favored feature of ozone here in the blue. This is one of the features that people are most excited about as the least ambiguous biosignature gas. However, there is this challenge that if the star is very active, then you will measure a different O3 abundance. And this is what I was telling you earlier about ways that we can have both false positives and false negatives, right, of biosignatures. So keep in mind that, that when you're looking at a spectrum, right, to ask yourself, what is the UV emission from the central host? And if it's an M star, what kind of M star? What kind of history did it have? What kind of flares is this planet really exposed to? These are all things that we have to keep in mind whenever we're studying the planets as well. All right, so to conclude, I'm going to put up my summaries here and ask a few questions that I'm sorry we won't get a chance to talk about in person, but maybe we'll do it. We can do it or during a question period or during one of the breakfasts or lunch, if that hasn't happened yet. Okay, so our understanding of planetary atmospheric escape and chemistry is controlled by the star's UV emission, possibly eroding the entire primordial atmosphere. However, but does it? We don't really know yet because we don't know fully what the UV emission is for all kinds of stars and trying to get those really energetic flares pinned down. And so there's a lot of work to be done there. M stars may be particularly challenging for habitable zone terrestrial atmospheres. Possibly, don't know. We're still working on it, of course. We haven't even discussed magnetic fields yet on these planets and the impact that they have. It doesn't mean just because a planet has a magnetic field, it doesn't mean that it's truly shielding the planet from mass loss, but that's a whole other talk with a lot of confusing data coming down the pipe from solar system observations. But do they have too many flares, these M stars? Is their quiescent emission too strong? And do they have CMEs, these coronal mass ejection? This is something that is a complete mystery. How many protons and high energy electrons are being spewed out with these giant flares? We really don't know, and are working hard to try to understand that. The third thing is different FUV to NUV ratios can produce, as I said, both false positives and false negatives. And so we really need to understand that for those of us interested in biosignatures. And in order to try and answer all of these, we really need more data. We need dedicated telescopes for both the very young stars and the very old stars, for disk dissipation studies, for old planets that we're currently studying. Really, this is just really the beginning. And so there's just so many questions. I think the answers are coming. Hopefully there'll be, some of you are working on this as well. And anyway, that's it. And I hope we have a chance for good questions and to talk some more. And certainly if not in this workshop, by all means, if you have any more questions, just drop me a line. Thank you.